By decreasing the core of the fiber, also we can get your VC value is equal to 2.405. This case also appears. Okay. So, we will solve the numericals by using the concept of your fibers, types of fibers. Okay. So, right on the first question. Written the first question. The normalized frequency, question number 1. The normalized frequency of a step index fiber, the normalized frequency of a step index fiber is 28 at 1300 nanometers wavelength is 28 at 1300 nanometers wavelength at 1300 nanometers wavelength 1300 nanometers wavelength full stop. What is the total number of modes? What is the total number of guided modes? Total number of guided modes. Total number of guided modes that can be supported by the fiber. That can be supported by the fiber. What is the total number of guided modes that can be supported by the fiber? That can be supported by the fiber. So, normalized frequency is given for a step index fiber, that is 28. So, from that we understand very clearly such that your V is greater than 2.405. Then it comes under the category of multimode step index fiber. For multimode step index fiber, the number of modes can be calculated by using a formula Mn is equal to V square by 2. So, substitute that particular value of your V, so that you will get the exact value like this. So, first question bhaiya. So, you are seeing about the first question, question number 1. So, if you write about the value given that normalized frequency is given, so value of V is equal to 28 and lambda is also given 1300 nanometers. So, 1300 nanometers is the value it is given. Then asking to find out what are the number of guided modes we are having. Mn is equal to how much? Bhaiya, the number of guided modes will be given as formula is equal to V square by 2. Sir, how I can use like this? In the question is specified only step index only. For step index, number of guided modes are going to be having V is greater than 2.405. It comes under the category of MMSI, multimode step index fiber. Then we can get the value of Mn. Mn is equal to V square by 2. Your V value is equal to 28 whole square by 2 is the value we are having. So, the respective value of Mn is equal to 392. 392 modes are present. Okay. So, number of modes we are having is equal to 392 modes we have. Complete copying. Complete copying. Correct answer. Shubhra Pandey, correct answer. Right. Read on the next question. Read on the next question. For a step index fiber to exhibit single mode operation. Next question. For a step index fiber to exhibit single mode operation. For a step index fiber to exhibit single mode operation. To exhibit single mode operation. When the core refractive index and radius r, and the core refractive index and radius r 1.46 and 4.5 micrometers respectively. 1.46 and 4.5 micrometers respectively. And 4.5 micrometers respectively, which is the relative index difference being, which is the relative index difference being, which is the relative index difference being 0.25%, 0.25%, 0.25%, comma, the cutoff wavelength is, the cutoff wavelength is. So, asking you to find out the cutoff wavelength. So, some of the given data is available, try to solve the question. I am repeating the question once again. For a step index fiber to exhibit single mode operation, when the core refractive index, and radius r 1.46 and 4.5 micrometers respectively, with the relative index difference being, 0.25%, comma, the cutoff wavelength is, asking you to find out the cutoff wavelength for the given question. Bhaiya, all of you please try to solve the question. Given that N1 is equal to 1.46, and he also given the radius means A value, the value of A is equal to 4.5 micrometers, the value of A is equal to 4.5 micrometers we are having. Next one is asking to find out the delta is also given, delta is equal to 0.25%, that means 0.25 upon 100. Asking to find out what is the cutoff wavelength lambda c is. What's the value of lambda c is present? This is the cutoff wavelength value. Asking for lambda c. So, we study in the classroom like this, cutoff wavelength lambda c, which operation it is? Single mode operation, that means SMSI. Bhaiya, we study in the classroom lambda c is equal to 2 pi A by Vc into numerical aperture Na. This formula is changes like this, that is equal to 2 pi A into N1 into root of 2 delta whole divided by Vc, that is equal to that of 2.405. That is a Vc value. Then your lambda c value is equal to 2 pi into A What is the value of A? A is equal to 4.5 10 to the power of minus 6 into N1. Your N1 value is equal to 1.46 under the root of 2 into, so 0.25%, that is equal to 0.25 whole divided by 100. The total value is divided by 2.405 we are having. So, use the calculator to find out the values. Please, all of you free to use your calculators, bhaiya. Lambda C is equal to, so lambda C is equal to, correct answers given by Shubhra, Komal, correct answers there. 1214 nanometers we are having. The value is equal to 1214 nanometers is the answer. Hope everybody in the class understood this numerical. Question number 2. Question number 2. Here seeing correct answer. Okay, right. Read on the next question, all of you. Question number 3. A step index fiber. Question number 3. A step index fiber has numerical aperture. Has numerical aperture 0.173. Has numerical aperture 0.173, 173, and supports 400 modes at a wavelength of, and supports 400 modes at a wavelength of 1.3 micrometers, at a wavelength of 1.3 micrometers, full stop. Calculate its core radius. Calculate its core radius. That is first question. Calculate its core radius, first question. Second question, to what value its core radius should be reduced? To what value its core radius should be reduced? Its core radius should be reduced so that it is a single mode fiber. It's a single mode fiber. So that it is a single mode fiber at lambda greater than or equal to 1.3 micrometers. At lambda greater than or equal to 1.3 micrometers. At lambda greater than or equal to 1.3 micrometers. 1.3 micrometers. I request all the students solve the question. All the students solve the question. Please use the concept that we study in the types of fibers and try to solve the question. Question number 3. If you see the question number 3, given that so what are the data it is given? The first thing it is given in the entire question is numerical picture is given. Na is equal to 0.173, supports a number of modes of 400, operating at a wavelength of 1.3 micrometers. At a wavelength of 1.3 micrometers. Okay, asking to find out the first question, that is bit A, asking the core radius. Core radius means A is equal to how much? Students, we obviously knows that this fiber is multimode fiber, need to find out the core radius. So we have to first of all know what's the value of your V. Okay, what's the formula we have? Mn is equal to V square by 4. Then your V square is equal to 4 into Mn, 4 into 400. Your V is equal to under the root of 1600. By under the root of 1600 means you are getting your value is equal to, so bhaiya this fiber is step index fiber na, it is specified in the single mode fiber which is calculated the core radius step index fiber bhaiya. Sorry for this one, I took the values of your gradient index fiber. This one is wrong, so this one is also wrong, and this one is also wrong, and here also calculation mistake we will get. So please see here, V square by 2, so 2 into Mn, that is 2. So V is equal to root of 800 we are having. The value of V is equal to root of 800 is present. Now what I am trying to doing is, I need to find out the your radius of the core. By V is equal to, study in the classroom, 2 pi A by lambda into numerical aperture. Then what is A? V into lambda divided by 2 pi into numerical aperture we are having. Then such A value is equal to V. V is equal to root of 800 into lambda. Lambda is equal to 1.3 into 10 to the power of minus 6 whole divided by 2 pi into numerical aperture. Numerical aperture value is equal to 0.173. Okay, sorry, 0.173. That value is equal to 0.173 we are having. So we can tell about that the value is equal to 0.173, 0.173, 173. Value of A is equal to. So request the students to calculate the value of A using the calculator. How much is the value of A we are getting? Value of A is equal to 33.82 micrometers. Correct answer, Komal. 33.82 micrometers we are having. The value is equal to A value. We are getting this one. Okay. Now see the question number B, Nana. What is asking is, what is the value of A to be decreased such that it can be operated in a single mode operation? It can be operated in a single mode operation. To what value of core radius should be reduced so that it is a single mode fiber at lambda is equal to 1.3 micrometers? Dear students, to convert your MMSI fiber into SMSI fiber, what is the value of V? 2.405. Value of V is equal to 2.405. So observe carefully after writing this point, V is equal to 2.405. So we understand very clearly such that it is given as like this. So here, bhaiya, your V is equal to 2 pi A by lambda into numerical aperture. Your A is equal to V into lambda divided by 2 pi into NA. Such A value is equal to V is 2.405 into lambda is 1.3 into 10 to the power of minus 6 meters whole divided by 2 pi into numerical aperture 0.173. The value of A is equal to. In terms of micrometers, you will get the answer. I am expecting answer from your side. Use the calculator, no problem. Use the calculator. All are mains part question only. Shubhra Pandey correct answer. Komal correct answer. How much is the value of A we are getting? Value of A. Yeah, correct answer. .87 micrometers. Komal, Yar Singh, correct answers. 2.87 micrometers is the correct answer we are having. Okay. Yeah, please copy this question. I will explain another question. Write down. Yeah, Somya correct answer. Shubhra Pandey correct answer. Write down. Next one. Next question. Question number 4. Calculate the number of modes. Calculate the number of modes for step index fiber. For step index fiber with the refractive index of core is 1.41 and claddie is 1.4 and claddie is 1.4 full stop. 1.4 full stop. The core diameter of the fiber is 15 micrometers. The core diameter of the fiber is 15 micrometers and operating at the wavelength of 820 nanometers. And operating at the wavelength of 820 nanometers. At the wavelength of 820 nanometers. Yeah, please solve the question, all of you. Please solve the question. So, what are the values we are having? Number of modes he was asking, that means Mn he was asking. So, modes for step index fiber is specified with refractive index of core is 1.41 and cladding is 1.4. Yeah, please solve the question. So, we solve this question with another color. So, here question number 4. Okay, question number 4. Right. Now, coming to the question number 4, what is the given that? Please solve it, all of you. Given that N1 is given 1.41, N2 is given 1.4, diameter is given 2a, diameter of the fiber is given, diameter of the core diameter of the fiber is given 15 micrometers, and operating wavelength is given 15 micrometers, and operating wavelength is given. Operating wavelength is equal to lambda. That lambda value is equal to 820 nanometers is given. So, given data. This is the given data, and from this given data he was asking to find out the your number of modes. Okay. So, number of modes we are having, that is called as Mn. Mn is equal to how much? Mn is equal to how much? Now, to calculate your Mn, definitely we need the value of your V, because of the step index fiber specified clearly. Your Mn is equal to V square by 2 is the formula. Such V value is equal to 2 pi a by lambda into numerical aperture. So, 2a is equal to 15 micrometers, then definitely we knows that your value of a is equal to 7.5 micrometers we are having. So, we calculate these values in the V formula, that is 2 into pi into 7.5 into 10 to the power of minus 6 micrometers into under the root of 1.41 whole square minus 1.4 whole square, which will gives the numerical aperture formula, divided by lambda 820 into 10 to the power of minus 9 nanometers we are having, and that lambda is nothing but an given in the question as operating wavelength. Now, we will get the value of your V, and that value of V is required. If you talk about the value of V, we get that V value equal to approximately it is getting 9.63 or 9.62 is the value we are getting. So, that value is equal to 9.62, equal to 9.62. Then we can write about the Mn. Your Mn is equal to V square by 2, and your Mn value is equal to V square by 2 in the sense means this is equal to that of 9.62 whole square by 2 is present. So, use the calculator and tell the values how much you are getting. We are getting approximately 46.3 we are getting. Sorry, Mn is equal to 46.3. By always write the complete number of modes. Complete number of modes means Mn is equal to 46, because 0.3 mode is not present. You consider the complete modes are equal to 46. Some books will write that 47 modes, writing in bracket as approximately, and that is also a true answer by a, no problem regarding that. But it's always prefer to write the complete number of modes we are having, that is equal to 46 complete number of modes we have. So, Mn is equal to 46 is the answer. A.R. Singh correct answer, Komal correct answer, Shubhra Pandey correct answer. We round off to 46 nana, instead of 46.38 or 46.27 like that. We round off to 46. Complete modes, exact answer, approximate answer is 47. Yeah, next question. Soumya correct answer, Mn is 46.35 is the correct answer. Alright, the next question, all of you. Question number 5. Question number 5. a graded index fiber has N1 is equal to 1.5, and N2 is equal to 1.45, Find the index at the midpoint on the radius that is r is equal to a by 2 nana. Midpoint on the radius, that is r is equal to a by 2. Please solve the question, all of you. Asking to find the index. Your index value is equal to n of r we are having. Okay, so solve the question. Please try to solve that question, guys. N1 is given 1.5, N2 is given 1.45. Okay, graded index fiber has N1 is equal to 1.5 and N2 is equal to 1.45. Find the index at the midpoint on the radius, that is r is equal to a by 2. So, what is the answer? Expecting from your side. Fifth question. Given that N1 is equal to 1.5, N2 is equal to 1.45, fiber is given as graded index fiber, alpha is not specified, your alpha is equal to 2 parabolic profile by default. Asking to find out what is the refractive index at midpoint on radius of core. That is already given. R is equal to which value? A by 2. R is equal to A by 2, specified in the question. Now, what you are trying to doing here is delta is required. Why? This is the formula, that is why n of r we study in the classroom, n1 into 1 minus 2 delta into r by a whole to the power of alpha whole to the power of 1 by 2. Your delta value is equal to n1 square minus n2 square divided by 2 n1 square. This value is equal to 1.5 whole square minus 1.45 whole square whole divided by 2 into n1 square. 2 into n1 square. n1 value is equal to 1.5 whole square. By substituting these values you get delta, and by calculating this delta using the calculator, value is equal to 0.003277 we are getting. 0.003277 we are getting. 0.03277 we are getting. I hope everybody in the class understood this. Okay. So we will get that value which is equal to that of 0.03277 is the value of delta. Substitute all the conditions in the given formula. N of R is equal to A by 2, midpoint. N1 is 1.5 specified in the question. 1 minus 2 into delta 0.03277. 0.03277 we are having. So we can write like this, that is equal to that of 0.03277 into R value is equal to A by 2 divided by A whole to the power of alpha whole to the power of 1 by 2 is present. A and A cancel out to each other. This value is equal to 1.5 into 1 minus this value is equal to alpha value is equal to 2 nana, alpha value is 2. Okay. So this value of alpha is equal to 2. Why parabolic profile? Parabolic profile in the sense means we know very clearly such that it is having alpha value is equal to 2. So 1.2, so use the calculator and calculate this entire part. So how much it is? 1 by 4 you are getting. 1 by 4 means cancel outing, that is 0.03277 by 2. Okay. So by 2 whole to the power of 1 by 2 we are having. So n of the value is equal to A by 2 we are having. This is equal to that of, what answer we are having? Answer is equal to 1.487. Yeah, correct answer. Somya correct answer. Radhika Devi correct answer. A.R. Singh correct answer. Shubhra Pandey correct answer. 1.487. 1.487. 1.487 is the answer we are having. I will explain a shortcut how to solve this question when it is given in the your prelims exam. Okay. Just observe here carefully guys. I am explaining you how to solve this question here using a shortcut procedure in the prelims. This is your cable, optical fiber cable having a core as well as claddie. It has a core and it has a claddie. By the center refractive index what you are having is called as 1.5, the refractive index of core. The refractive index of core is equal to 1.5 and here the edge is equal to 1.45, asking at the middle. The middle is nothing but an average of these two, that is 1.5 plus 1.45 by 2. What you are getting approximate answer is 1.48 nana. Okay, 1.48. That is how we can solve the question without doing all these things when it is asked in the prelims. You can just take an average of those two refractive indices. At center you will get the value, and the center value what you are having is equal to the refractive index, close to the refractive index, not exact value, close value you will get. Okay. Next question solve by yourself only. Next question solve by yourself only. Right. Please copy the question, all of you. Next question. A fiberglass of parabolic profile, a fiberglass of parabolic profile with N1 is equal to 1.4, with N1 is equal to 1.4, comma, delta is equal to 0.31, delta is equal to 0.31, and it is operated at lambda is equal to, and it is operated at lambda is equal to, operated at lambda is equal to 1.5 micrometers, 1.5 micrometers. What is the large core radius? What is the large core radius for which this fiber is single mode? What is the large core radius for which this fiber is single mode? For which this fiber is single mode? Fiber is single mode. Okay, right. So please see here. You need to tell the answer, repeating the question once again. I am repeating the question, expecting answer from your side. A fiberglass of parabolic profile with N1 is equal to 1.4, comma, delta is equal to 0.31, and it is operated at lambda is equal to 1.5 micrometers, operating at lambda is equal to 1.5 micrometers, full stop. What is the large core radius? What is the large core radius for which this fiber is single mode? Large core radius for which this fiber is single mode, for which this fiber is single mode. Asking to find out the radius, nana. A is equal to how much? Given fiber is not step index, na. Given fiber is graded index. How we knows that parabolic profile is given? For parabolic profile we call it as graded index. Okay, we call it as graded index. Right, please. Question number 6. Given that parabolic profile alpha is equal to 2, first point. Next, he give the value of N1, N1 is equal to 1.4 and delta is equal to 0.31. N1 is equal to 1.4 and delta is equal to 0.31. Lambda is equal to 1.5 micrometers we are having. This is the given value. Your lambda is equal to 1.5 micrometers. What is the large core radius for which to be operate in a single mode? What is the value of A? To have the operation called as which operation by a single mode operation is required. For single mode operation is required. Just try to understand one simple point here after copying this part. Bhaiya, we study in the classroom your VC is equal to 2.405 into 1 plus 2 by alpha whole to the power of 1 by 2. Study in the classroom. If you talk about the VC value, we can write like this. Your VC is equal to 2.405 into 1 plus value is equal to 2 by 2 whole to the power of 1 by 2. So, your VC is equal to 2.405 into root of 2 we are having. So, root 2 value. That means 1.414 is multiplying with the 2.405. So, VC. Now, you want the large core radius. What is the formula we studied? That is A is equal to, if you observe this formula, we are having like this. The value is equal to VC into lambda divided by the value is equal to 2 pi into numerical aperture. So, A is equal to this formula can also written like this, that is equal to VC into lambda whole divided by 2 pi into numerical aperture n1 into root of 2 into delta. Everybody in the class get a clarity regarding this. What is VC? VC is equal to 2.405 into root of 2 into lambda 1.5 into 10 to the power of minus 6 micrometers whole divided by 2 pi into n1 diya bhaiya, n1 is equal to 1.4 hai, root of 2 into delta diya bhaiya, delta diya is equal to 0.31. So, this value of A we are having is nothing but an required radius of the core. We will get in terms of micrometers. In terms of micrometers, you will get the answer. So, the answer we are having 8.01 micrometers. 8.01 micrometers. Remaining students, please calculate and tell the answer. Use calculators and tell the answer. We start the next concept. Yeah, what is the answer you are getting? What is the answer? Students, use the calculator and tell the answer. Waiting for the response from your side. Only 2 students will put a message. Solve it. Nobody will tell the answer, bhaiya. We need to solve it. Because the solution is not with me also to tell the answer. Yeah, we will start the next concept. Yeah, how much is the answer you are getting? So 0.736 micrometers, you are getting the answer. 0.736 micrometers is the answer we are having. So this is the topic for types of fibers. See, as per the syllabus, we completed the 3 parts, and now we are going for the next one, that is called as attenuation. The next part is called as attenuation. Next topic is called as attenuation topic. Attenuation is denoted by alpha, is equal to alpha we are having. So we can write like this: an optical fiber of length L, refractive index of core is N1 and clad is equal to N2, and this is called length of the fiber given as L. Input power that is passing into a fiber is called as P in. The output power getting out of the your fiber is called as P out. Actually, the dream of every engineer is your P out should be greater than the P in. We expect like this, because as an engineer we want to give a small amount of power given to the fiber, and we want to get a huge amount of output power has to be expecting. But God is crazy, He never gives like this, putting small efforts, don't expect big results by ya. Okay. So P out is going to be not greater than P out, then at least we think like this: your P out must be going to be equal to P in, and that is also not possible. It is not also not given. For your efforts, getting your results is not done. Then what happened is, all the time you get P out is less than P in only. Why? Because means your fiber was going to be having the material will absorb some of the light. Then what is the output power we are getting is always less than your P in, input power. That is called as loss. That is called as loss. Actually expecting to get more gain, no gain. At least I give some P in power, please give P out power. No, it is also not possible. But what it is giving? It is giving you P out should be less than P in. And how much amount of power is absorbed, or how much amount of power is less power you are getting, output power is said to be called as loss. That loss is also called as attenuation. It is called as attenuation we are having. Okay. Now please see here, all of you, talking about the attenuation we are having. So this is the first thing that you must be observed clearly. So P out must be value getting is less than P in. So we write your alpha. Alpha is given as input power divided by output power, which is called as loss. So your alpha is always represented in terms of dB. Alpha is written in terms of dB. Writing the same thing in terms of dB, then it is called as 10 into log of power ratio of output input power by output power of base 10 in terms of dB. But this attenuation is always measured for the unit length of kilometer, that is dB per kilometer. This length L was taken in terms of unit length. Unit length means L is equal to, generally unit length we considered without giving anything means we consider equal to 1 kilometer by a. So unit length by default, explaining here, by default your unit length was considered to be equal to 1 kilometer we are having. So 1 kilometer is said to be called as the unit length we are having. So that is nothing but an 10 by L. L is called as the unit length into log of value is given as P in by P out, which is given as dB per kilometer. So this is the formula for attenuation, because this is a line, you are having the fiber optical cable is a link. If you define for 1 kilometers, the same attenuation has to be present for the 100 kilometers of link also. Because of distributive parameters we are having, we can take that for 1 kilometer if you define the characteristics, because the cable is uniform, we know obviously, because of uniform cable it is having the same amount of attenuation throughout the length of the fiber. So that is what the fiber is always, attenuation is always defined for unit length or defined for unit kilometer we are having. So next important point I will tell to you here is writing the power, what is the power we are having, that is called as the loss, and that formula will going to given as like this, which is indicating in the value. So please see here, whatever the value we are having is alpha, alpha is equal to 10 by L, 10 by L into log of P in by P out, P in by P out of base 10. I forgot to write about the base 10 here, of base 10, base 10 it is present like this. Now see carefully, alpha is equal to 10 by L, log of P in by P out of base 10 is present. L goes to other side, alpha L divided by 10. So log of base 10 P in by P out, we get like this, 10 to the power of the value is equal to alpha L by 10 we are having, that is equal to P in by P out. I want to calculate the output power, therefore your P out is equal to P in upon 10 to the power of alpha L by 10, then your P out is equal to P in 10 to the power of minus alpha L by 10. This is the output power in terms of watts we are having. This is the formula of your alpha attenuation in terms of dB per kilometer. This is the output power formula in terms of watts we are having, how much amount of output power. Observe carefully, your output power is affecting by the attenuation offered by the fiber and also depending upon the length of the fiber. More the length, then amount of power obtained, output power will be less, and it is also depending upon the input power also. If you are giving very small amount of input power, sometimes your output power may not be going to absorb also, may not be obtained also, output power will be 0 also. This is all about the attenuation we are having. Next point I want to tell to you is explaining here, these are the formulas of calculation of your attenuation and output power. Next formula, in optical communication system, alpha depends upon the wavelengths, alpha depends upon the wavelengths. At a particular wavelengths we are going to be having the attenuation is very less, and those things we will study in the classroom. Now more important thing that we need to understand is, in entire optical communication system, alpha depends upon the wavelength. So depending upon the wavelengths, different wavelengths, we are having different your attenuations are offered at different wavelengths we are having. So I will explain that with a small graph. You please copy it, and I need to tell you about the point also here as a note to you. Okay, after that diagram I will tell the note to you. You please copy this one. Once copying is completed, please put a message in the chat box. Please put a message in the chat box. See here, next topic. I am drawing the sketch. This is your lambda in terms of nanometers. This is alpha dV per kilometer. dV per kilometer. Just observe it. In between 800 to 900 nanometers, at 800 to 900 nanometers, we are having a loss of 2.2 dV per kilometer. This is called as the first low loss window. It is called as first low loss window. In the first low loss window, laser is fabricated. Laser is fabricated at 850 nanometers. The reason for making the laser to be fabricated here at 850 nanometers is, it is very simple, such that at 850 nanometers, it is very simple such that if you see the copper wire, up to there we have a copper cable, bhaiya, copper cable used for telecommunication. If you see the copper cable, that copper cable is going to be having a loss of 20 dB per kilometer. When compared to 20 dB per kilometer, this loss is 2.2 dB per kilometer, almost 10 times it is decreased. Then the engineers felt very happy such that kitna loss kam ho gaya, bahut khushi ho gaya, and they designed the laser at 850 nanometers and operated. And later on they are going to be increasing the frequency, and that is increasing the wavelength by decreasing the frequency. Then they can find out another interesting thing called as, at 1300 nanometers they can find out the loss of 0.6 dB per kilometer. Then also scientists felt very happy such that, array 13 nanometers your amount of loss offered is very less. They are calling this as a second low loss window. Second low loss window. At a second low loss window, what they done is, they are going to be using fibers at second low loss window, which are called as shifted version, that is dispersion shifted fibers are used here. So the dispersion is shifted here, the dispersion shifted fibers, I will explain in the classroom. So dispersion shifted fibers has came into the picture, loss become less, dispersion shifted fibers we are having. Because this concept is not yet completed, bhaiya, what is dispersion I will explain to you, and how it is shifted also I explain to you. Just after the completion of this concept, I will tell the causes of attenuation, there you understand. So what we came to a picture is very simple, such that in the first low loss window, you are designing the fiber, fabricate the laser, and in the second low loss window, you observed carefully, you are having a fibers which are operating at this wavelength. The fiber is going to be having a shifted, dispersion shifted fibers are present. Now coming to the third low loss window, bhaiya, just concentrate for 2 minutes of time, very simple it is. So talking about the third low loss window, at third low loss window, it is really shocking for everyone. At 1500 nanometers, you can find out such that the loss is equal to 0.2 dB per kilometer. If you operate your optical fiber cable systems at 15 nanometers, the amount of loss offered is becoming very less. If the loss offered them is very less, then automatically what happens is, the number of repeaters will be less, the delay will be less, then the cost will also be very less. So we can going to be getting an effective way of communication with low loss. This is one of the beautiful advantages that we studied in our optical communication system also. I told in our previous classes such that optical communications offers a very huge bandwidth, and optical communication will also have very less loss. See, where is 20 dB and where is 0.2 dB per kilometer bhaiya? Copper cables offers 0.2 dB, sorry, 20 dB per kilometers, and your OFC cables are offering only 0.2 dB per kilometer when you operate at 59 nanometers. So that's why this 59 nanometers is called as the third low loss window bhaiya. It is called as third low loss window, which is called as third low loss window we are having. Is called as third low loss window is present, and here it is using WDM techniques are used. The WDM techniques means wavelength division multiplexing techniques are used. So where this is the important one, that's the milestones, we call them as a milestones. So these are the milestones we can going to be find out in the technology wise when you are talking about the optical fiber cable. So by this we can see the drastic change in telecommunication. Entire copper cables are replaced by the OFC cables in a very short span of time because of less loss and also offering more amount of bandwidth. All the networks that copper networks are going to be public switching networks are completely converted into the OFC cables. Then the revolution started at that time. So many of the students will also know about that when you are maybe at the in the 10th class, or maybe when you are in at the age of at the 9th or 8th class also, you can find out the Reliance has came into a picture and has the light all the over the India with optical fiber cables. Okay, so that is what called as a network, building a network, building the own network, and that network can be given lease to the remaining one. That's why Jio is a more powerful one bhaiya when compared to that of the remaining networks. The reason is I am not promoting anything, just I am telling the concept. What happened generally is they laid the cable in very 2001 at that stage only they laid the cables, OFC cables. Now it is 2023, 2001 to 2023, approximately 22 years we are having. 22 years the lifespan of the fiber is running in the same way. The bandwidth offered by them is also the same, and the fiber life is also more than 100 years it is present bhaiya. It's not like copper cable, there is no corrosion, nothing, it is in the ground itself only. Right. So just maintenance is required, the maintenance is required, and whenever we dig it, we have to cut the wire, means we have to just make a splicing there, maintenance is required. So this is what the case we are having, the losses alpha in terms of dB per kilometer we have. So that losses alpha dB per kilometer is obtained. So I can explain these losses we are having with a small table. Try to understand everybody in the class, very simple Nana. So I can tell in this way. This is called as wavelength, dear students, wavelength in terms of nanometers we are having. It is called as alpha, that is attenuation. So we can write the wavelength here up to here. It's called alpha. Alpha is written in terms of dB per kilometer we are having, dB per kilometer. And the remaining one is called as percentage of loss, that is loss percentage. So percentage of loss we are having. So once we talk about this part, we can clearly understand that how much is the attenuation offered by the fiber. Okay. So please see here, the first thing is we are having from 800 to 900 nanometers. In that we are operating at 850 nanometers, Nana. At 850 nanometers we are operating. Your loss is equal to 2.2 dB per kilometer. Please see from the chart, from chart we got it, it is 2.2 dB per kilometer. Percentage of loss, Nana, percentage of loss is equal to 20% of loss we are having. So this is what the amount of loss we are having whenever we are using at 850 nanometers. So next one is we will see about the 1260 to 1360 nanometers we are having in terms of nanometers. That is at 1310 nanometers, which is called dispersion shifted fibers. The loss was drastically decreases, that is from 2.2 to 0.6. Then we are having the percentage called as 6% of loss we are having. So next important one, it is most important one, that is equal to 1500 to 1600 nanometers we are having, operating at 1550 nanometers bhaiya, at 1550 nanometers. Students obviously knows about this one. At 1550 nanometers we are having. We are having a loss of 0.2 dB, amount of percentage of loss is 2%. Out of the total power you are sending, only 2% of power is going to be wasted, remaining everything is obtained as the output power we are getting. So, only small amount of percentage of power is losing. So, loss is very less if you are operating at 15 nanometers, okay, 1550 nanometers. So, see this point by a modern telecommunication, just try to understand this, asked many times in the exams and in the interviews also. So, modern telecommunications, what are the modern telecommunications we are having right now, like cellular or the optical communication, or we can tell about the optical signals to be carry in modern telecommunication. Excuse me. So, modern telecommunications uses 193.1 terahertz at 1552 nanometers. At 1552 nanometers, we are using 193.1 terahertz we are having. Already I told in the classroom, we give most importance for the wavelength, not for the frequency. But this is a very good question that asked in the interviews also, what is the frequency we are having, using the entire modern telecommunication using the frequencies. So, this is completely a small spectrum we have. I wrote it here and I explain next one about the causes of attenuation. And after completion of copying this part, please put a message so that I can tell the note to you. You can write the note of this attenuation. Okay, Bhaiya. ARCing, the meaning for laser fabricated means at that wavelength we are going to be, the laser is operating at a wavelength of 850 nanometers, we are fabricating the laser to generate that particular wavelength, 850 nanometers of wavelength. That is why it is called laser is fabricated. So, now you have designed a laser and that laser will generate the wavelength of how much? 850 nanometers of wavelength will be generated. Bhaiya, this loss is 5%, I wrote here 6% it is. This is 5%, not 6% we are having. This is equal to 5%, 20%, 5% and 2%. If it is complete copying, please put a message, I will explain the points and we will start with the causes for attenuation. Write down the first point. Write down the first point. Attenuation is defined as ratio of input power to that of output power to that of output power Next, attenuation has several effects on performance. Attenuation has several effect on performance, including first point, reducing the bandwidth, second point, reducing information transmission rate, Point number 3, decrease overall system efficiency. Reducing bandwidth, first point. Second point, reducing information transmission rate. Third point, decrease overall system efficiency. Next point, in fiber optical communication, the attenuation of light propagating through glass, depends on the wavelength. Right. So I hope everybody in the class understood this. But one simple topic is left over here, that is called as your dispersion shifted fibers. I will definitely explain this to you, dispersion shifted fibers to you, when we are discussing about the dispersion concept. So next one is about the causes of attenuation. So we can tell the causes of attenuation. So we are discussing here, it is called causes of attenuation. Next topic, which is given as causes. What are the different causes for attenuation? So causes for attenuation. The first point that we can see about the causes for attenuation is, first one is absorption loss. It is called as absorption loss. Second one is called as scattering loss. We are having scattering loss. Third one is called as waveguide bend loss. By bending the fiber also we are getting some losses, which is called as waveguide bend loss. Fourth one is called as core and clady loss. core and clad loss we are having. Fifth one is called as dispersion. It is called as dispersion. Fifth one. Sixth one is said to be called as the coupling losses. It's called as coupling losses we are having. This is sixth one. So these all things are going to are the reasons for having the losses in your optical communication system. We will study in detail about each and every one. What is absorption loss, what is scattering loss, what is waveguide bend loss, core and clad loss, dispersion and coupling loss. So I can start explaining you about the absorption loss. Okay, explaining you about the absorption loss we are having. So bhaiya, time is also less. Even I start this topic, it takes some amount of time. We will see the topic in the tomorrow's class. If you have any doubt, you can please put a message for that one. Okay. So in the tomorrow's class, we will discuss about the absorption loss, how the absorption loss is there, and all those things we will study in the tomorrow's class. Okay. Good night. Jai Hind. Thank you. Thank you, Anuj Naik. You are most welcome. Exactly correct. You are saying exactly correct. What you said is that message signal is carried by 850 nanometers of wavelength of light will carry that message signal from one point to the another point. It will carries. At 850 nanometers, what happened? The amount of loss offered is very less. Is very less we are having. Okay. I hope it's clear. Clear na? Okay. Okay, you are seeing. Most welcome, you are seeing. Okay, students, that's all for the day. We will see the remaining things in the next class.